during the
சரி ஐயா, இது வந்து என் கையில இல்ல ஐயா.
பண்ண முடியாது. It is fantastic arrangement. But unfortunately we sat on that row.
புரியுது ஐயா. வேணும்னா இப்படி வந்து உட்காந்து போங்க. தெரியல. சரி.
கரெக்டா அந்த போர்டு இருக்குல்ல.
Something to quite find out. If someone has library. Just before.
நண்பர்களே, நிகழ்ச்சி துவங்க இருக்கிறது, தொடர இருக்கிறது. ஆங்காங்கே உரையாற்றி கொண்டிருப்பவர்கள் அவர் இருக்கையில் அமருமாறு கேட்டுக்கொள்கிறோம்.
சயின்ஸ் பார்க்க மெம்பர் ஆகிறதுக்கு நேம், மொபைல் நம்பர், இமெயில் ஐடி மட்டும் வித் அந்த லொகேஷன் தாம்பரம்னா தாம்பரம் இந்த மாதிரி கான்டாக்ட்.
அரங்கத்திற்கு வெளியே இருக்கும் நண்பர்கள் தயவு செய்து இருக்கையில் வந்து அமருமாறு கேட்டுக்கொள்கிறோம். இந்த நிகழ்ச்சியை பற்றிய உங்களது கருத்தை உங்களிடம் கொடுக்கப்பட்டிருக்கும் அந்த பேப்பரில் எழுதி எங்களிடம் ஒப்படைக்குமாறு கேட்டுக்கொள்கிறோம். நீங்கள் அரங்கத்தை விட்டு வெளியே செல்லும் பொழுது இந்த நிகழ்ச்சியை பற்றி உங்களது கருத்தும், எதிர்காலத்தில் தமிழ்நாடு அறிவியல் இயக்கத்தில் எந்த மாதிரியான நிகழ்ச்சிகளை நீங்கள் எதிர்பார்க்கிறீர்கள் என்ற ஆலோசனையையும் நீங்கள் எழுதி எங்களிடம் கொடுத்து விட்டால் எங்களுக்கு மிகவும் பயனுள்ளதாக இருக்கும். Yeah. Friends, you can write your feedback on a sheet of paper that's available in your pad and hand it over to us. That will help us to organize better. கூட்ட தலைவர் கேட்டுக்கொண்டதற்கிணங்க உங்களை எல்லாரும் தமிழ்நாடு அறிவியல் இயக்கத்தில் உறுப்பினராக இணையுமாறு அழைக்கிறோம். உறுப்பினர் படிவம் தமிழ்நாடு அறிவியல் இயக்கத்தினுடைய இணையதளத்தில் இருக்கிறது. உறுப்பினர் கட்டணம், உறுப்பினர் நுழைவு கட்டணம் 30 ரூபாய். உறுப்பினர் சந்தா 30 ரூபாய் தான். நாங்கள் நிச்சயமாக தொடர்ந்து இது போன்ற நிகழ்ச்சிகளை நடத்துவோம். உறுப்பினரான பிறகு நீங்கள் ஒவ்வொரு குழுவாக பிரிந்து ஒரு கிளையாக செயல்படலாம். குறிப்பாக கல்வி நிறுவனங்களில் அங்கேயே நாங்கள் வந்து இது போன்ற நிகழ்ச்சிகளை நடத்துவதற்கு ஏற்பாடு செய்கிறோம்.
நண்பர்களே, நிகழ்ச்சியை நாம் தொடர இருக்கின்றோம். அனைவரும் உங்களுடைய இருக்கையில் அமருமாறு மிகவும் பணிவன்போடு கேட்டுக்கொள்கிறோம். அனைவரும் இருக்கையில் அமருங்கள். நிகழ்ச்சியை மீண்டும் துவங்க இருக்கின்றோம். இது மூன்றாவது உரையாக நம்மிடத்தில் பேச இருப்பவர் டாக்டர் ஸ்ரீராம். அவர் சென்னை ஐஐடியில் இயற்பியல் துறையில் பேராசிரியராக பணிபுரிகின்றார். அவர் டாக்டர் டி.ஆர். கோவிந்தராஜன் பேசிய பொழுது குறிப்பிட்ட பெக்கன்ஸ்டைன் அவர்களிடம் ஆய்வுக்கு பின்னாலான மாணவராக பணிபுரிந்திருக்கின்றார். பெக்கன்ஸ்டைன் பிளாக் ஹோல் தெர்மோடைனமிக்ஸ் என்பதில் ஆய்வுகள் செய்தவர். அவரும் டாக்டர் ஸ்ரீராம் அவர்களும் காஸ்மாலஜி குறித்தும் இந்த பேரண்டம் எவ்வாறு உருவானது என்பதை குறித்தும் ஆய்வு செய்பவர்கள். ஸ்டீஃபன் ஹாக்கிங்ஸ் அவர்களுடைய முக்கியமான பணிகளில் ஒன்று ஆரிஜின் ஆஃப் யூனிவர்ஸ், இந்த பேரண்டத்தினுடைய தோற்றம் என்பது குறித்ததும் இருந்தது. டாக்டர் ஸ்ரீராம் அவர்கள் இப்பொழுது நம்மிடம் பேசப்போவது ஸ்டீஃபன் ஹாக்கிங்ஸ் அவர்களுடைய கருத்து, அதாவது இந்த பேரண்டத்தின் துவக்கம் குறித்து ஸ்டீஃபன் ஹாக்கிங்ஸினுடைய கருத்துக்களை குறித்து டாக்டர் ஸ்ரீராம் அவர்கள் நம்மிடம் இப்போது உரையாற்றுவார். டாக்டர் ஸ்ரீராம்.
Thank you. I should begin by apologizing for not being able to speak in Tamil. It's very difficult for me. I can converse in Tamil, but it's very difficult for me to convey scientific ideas precisely in Tamil. So I'm going to stick to English. During the interaction session, I'll be glad to answer. I'll try my best to answer any questions you may have in Tamil if needed. I should begin by thanking various members of the Tamil-Nadu Science Forum for inviting me to give this talk. Cosmology is sort of underrepresented in Chennai. I try not to give up an opportunity to speak on cosmology here in any forum in Chennai. Earlier this year, in March, we lost a theoretical physicist of the highest caliber in Stephen Hawking. Hawking made a variety of contributions in various topics in physics, largely on issues related to gravity and quantum theory, as Professor T.R. Govindarajan highlighted. Arguably, his most significant contribution, as highlighted in these stamps, which were put out by Isle of Man, was his discovery of thermal radiation from black hole, which is nowadays referred to as Hawking radiation in his honor. He has made a variety of other contributions, notably certain ideas in cosmology, which are related to what are known as the origin of perturbations in the universe. I'm using a technical word called perturbations. I will try to explain this as we go along. It will become clear, hopefully, by the end of the talk. And he has also made some proposals of the origin of the universe itself. It is a lot easier to explain issues related to the origin of perturbations, origin of structure in the universe. How did the galaxies form, for instance, or the large-scale structure, which are collections of galaxies form. Hawking made significant contribution to this. In this case, he was not the sole contributor like it was in the case of Hawking radiation, which was a phenomenal discovery. There were many other contributors, but nevertheless, Hawking had made a contribution. And a contribution which is somewhat much more technical and difficult to explain, and therefore I will relegate to the real end of the talk, is about the origin of the universe itself. I will spend a lot of time on the origin of perturbations because it can be compared with observations. In contrast, his ideas on the origin of the universe are still theoretical in nature, and I believe we are still very far from comparing with experiments or actually observations in this context, since we are talking about the universe itself. So, also, I'm assuming that many of you are not quite familiar with the cosmology as it stands today. Cosmology is the physics of the universe as a whole. We are not interested in this solar system or this galaxy or this planet or even collections of galaxies. We are interested in the behavior of collections and collections of galaxies. You will understand what I mean by that as I show some pictures and movies as you go along. Therefore, what I intend to do is spend a lot of time explaining what is modern cosmology, popularly referred to as the hot Big Bang model. One of the significant additions to this conventional hot Big Bang model is something called the inflationary paradigm or the inflationary scenario, according to which the universe is supposed to have expanded very rapidly during the very early stages of its expansion. I will talk about the fact that the universe is expanding today, if you're not familiar with it already. And this is where Hawking comes in. So I'm going to start by first, as I will illustrate, I will make a few remarks which Professor Govindarajan already made about Hawking's academic history. And then I will go on to explain, in order to understand our universe, how it started, how is it evolving, etc., we need to understand what the universe contains. So I will start with a survey of the universe itself, what it contains. I mentioned it contains, collections and collections of galaxies, and the challenge is to understand how these originated and why do they have the structure that they have today. So I will talk with a survey of the universe, and then I will tell you about the composition of the universe. What does the universe contain? Obviously contains what we call matter, that you and me are made of, and it also contains light, which the physicists refer to as radiation, and there is an extremely important ingredient in this radiation, which is something called the cosmic microwave background, which, as I will describe, allows us to understand how the universe evolved during the very early stages. The fact that you have radiation and you have matter, immediately tells you, because of the behavior of these quantities, as I will discuss, that the universe began in a very hot, dense phase. And universe is expanding, as I will explain. And if you run this expansion backward, it should have started somewhere, which is referred to as the Big Bang. There are misconceptions that can arise because of this name. These terms are catchy, but there can be misconceptions that can arise. I will try to explain, clarify those misconceptions as we go along. So you have supposed to have had a Big Bang, the universe was hot, and it is expanding. That's the picture we have today, roughly, and it is called as the hot Big Bang model. And onto this hot Big Bang model, we will introduce something called the inflationary epoch. Okay? Inflation can be bad for the economy, it is good for cosmology, and what it means is that you need an epoch of very rapid expansion. I will explain this as I go along, and it is during this epoch there are supposed to be quantum fluctuations. Professor T.R.G. mentioned about quantum mechanics. It plays a very significant role, and this is also where Hawking comes in. And it is these quantum fluctuations, as I will discuss, which are supposed to have generated you and me today, essentially. And then I said, this part is relatively easy to explain. It's a lot more conceptually difficult for me to discuss Hawking's ideas on the origin of the universe, but if there are undergraduate students who know something like a Schrodinger equation, I can try to explain in the best I can. I do so in a couple of slides, and I will close with a status of these Hawking's ideas and a brief outlook. So a few words on Hawking's academic history. This is a very famous photo of Stephen Hawking that was taken by BBC. And here's a very quick academic history. He did his PhD on general relativity, issues related to general relativity, under the supervision of someone by name Dennis Sciama at Cambridge. And then for a while, he spends time as a research assistant. He didn't have a permanent job, okay, from roughly something like 67 or 68 until 73 when he discovered Hawking radiation. They immediately gave him a job. And he was the professor at Cambridge. And then, the ideas that I'm going to talk about were actually done largely by his co-workers and students, James Hartle and Halliwell, okay? And this was done in the mid-80s. He was at Cambridge for most all his life, essentially, until he passed away earlier this year. So, for those who are technically interested, I am going to talk about these 3 papers of Hawking. The first paper is largely what I'm going to talk about. The second 2 papers are highly complex, and if there is specialized audience who are interested in audience who are specialized and who want to understand this better, I will be glad to speak to them after my talk. Towards the end of the talk, I will list some popular books which you can refer to. So let's start with a survey of the universe. We need to understand, before we understand what cosmology is, we need to know what the universe contains. Well, you would have heard about our solar system, and for instance, Professor Govindarajan mentioned that there is a black hole, a 1 million solar mass black hole, which is located in the direction of Sagittarius in our galaxy itself, that is in the center of the galaxy. And this is a picture of our galaxy. We have hardly reached the edges of the solar system. Obviously, this is a picture not taken from outside the galaxy, from inside the galaxy. There is a satellite called the Cosmic Background Explorer, or the COBE satellite. We will encounter the satellite again later. What it did was that it had an infrared camera and or a telescope, and it turned all around the sky and got this image. And our galaxy is like a Keralite appam. It's like the appam. There is a bulge in the middle, okay, which is where the supermassive black hole that Professor Govindarajan was mentioning about rests, okay, and it contains many stars, such as the sun. The sun is almost an irrelevant star. It is important for us. On the global scheme of things, it's an irrelevant star. And it contains, it is about 15 kiloparsec. I'm going to introduce a term called parsec. It is about 3.26 light years. I presume you heard of the idea of a light year. A light year is the distance traveled by light in a year. And you know that the speed of light is 3 times 10 power 5 kilometer per second. So you multiply it by the number of seconds in a year, you will get this distance. And parsec is 3.26 light years. It is a strange unit which astronomers use. I will just continue with my discussion. We can discuss later as to why the parsec arises. So it contains about 10 power 11 stars, such as the sun, and its mass is about 10 power 12 solar masses. That is as many masses as the sun's mass. Now, that's our galaxy. What do you have beyond that? There are some what are called satellite galaxies near us, but they are irrelevant. They are very small. One of the largest galaxy, which you can see through a small telescope as a buzzing hive of activity, is something called the Andromeda galaxy on the left, which is at a distance of 700 kiloparsec. Let me remind you of the unit. A parsec is 3.26 light years, and a light year is, distance traveled by light in a year. And there are many such galaxies. About 30 odd galaxies form something called a local group. There is another galaxy on the right, okay, which is called the Triangulum galaxy, and it is at a distance even larger. I presume all of you know units like kiloparsec is 10 power 3 parsec, like a kilometer is 10 power 3 meter. And we have here a galaxy at a distance of 1.3 megaparsec. A mega is 10 power 6, a million parsecs. So you are talking about really large distances, but we still haven't reached cosmological scales. So what do you have when you see, beyond? Well, the first thing you see is varieties and varieties of galaxies. That's a galaxy on the left, which is very similar to our galaxy, okay, seen sideways. And there are galaxies with barred, they have a spiral shape, and there are very peculiar galaxies, some of which are illustrated here, and they have certain nomenclature. There is a specific nomenclature to name them depending on who first observed them, etc. Now, what you see is that I mentioned there is a group of about 30 galaxies, which our galaxy is a part of. What you find is that our local group, as we call it, of this about 30 galaxies, is part of a much larger cluster of galaxies. Now you're talking about really extremely large scales. You know, on the leftmost is something called the Virgo galaxy. It consists of more than 100 galaxies, and its size is about 20 megaparsec across. We are talking about really large distances now. In the middle, on the right, we have illustrated each of these extended objects in this is a galaxy. I hope you appreciate that. Again, I should emphasize, we are trying to understand the physics of the universe as a whole. We are not interested in how this galaxy behaves or that galaxy behaves. We are interested in understanding how this collection of all these galaxies put together behave. Okay? So you have something called a coma cluster of galaxies in the middle, and you have another Hercules cluster of galaxy, and all of them contains about 100 to 1,000 galaxies, and they have scales anything between 20, a few tens of megaparsec across. So what do you have beyond them? This is one of the deepest views in space, which was provided to us by the so-called Hubble Space Telescope, and each extended object here is a galaxy. So when you look at the largest span in the sky, you are seeing clusters and clusters of galaxies. There are millions of galaxies surrounding us. And I will quickly provide what are the largest views in space in a matter of minutes. What people did since the 90s is they did this great attempt of surveying the universe as a whole. So you build a reasonably powerful telescope, you keep observing as far as your resolution of the telescope permits. And one of the earliest survey is called the 2-degree field survey. There is an atom in the middle, which is our galaxy. What they did was that they took a square degree north above the galaxy and a square degree in the sky south of the galaxy in these two directions, conical directions, and observed galaxies to the extent that their power of the telescope permitted. And this is what they obtained. What you have here is each dot, again, do not worry about the color of these galaxies, the color of these dots. They represent galaxies of different properties. It does immaterial for our discussion here. What you see is a relatively, on a suitably large size, the galaxies are uniformly distributed. Again, let me emphasize what is our goal. Our goal is to understand the physics of the universe as a whole. And when we see around us, there is matter which is clumped. There is a galaxy here, there is a galaxy there, and there's a galaxy far away, and there are clusters of galaxies. But it doesn't seem that the universe is smoothly distributed. The matter is smoothly distributed in the universe. The point is as follows. If I draw, there are people distributed here, and if I start drawing circles of say 1 meter across radius and I place it here, evidently if you place it here in the middle, there'll be none, while I place it in some corner there is a large number of people. But if I draw a reasonably large circle, I presume you will agree there is an uneven distribution here. It's not ideal, but I presume you would agree if you draw a reasonably large circle and you ask whether the same number of galaxies are present in the circle at a reasonably large radii, there will indeed be enough, roughly the same number of people present here. In the same sense, what we find in the universe is that if you draw a sphere of radius of the order of 100 megaparsec or so, let me remind you the numbers again. Mega is 10 power 6, parsec is 3.26 light year. Light year I have emphasized already a couple of times. Over such a large scale, if you place a sphere, you find that the distribution of matter in the universe is roughly uniform. So what cosmologists, theoreticians, try to make simplifying assumptions to understand our universe. One of the simplifying assumptions we make is the universe is homogeneous. All it means is that the matter the galaxies are distributed uniformly in the universe. Then the challenge is to explain why did these become clumpy. We will divide this problem before us, the observations that we have, into two parts, a smooth universe, and then we will try to understand how clumps formed within this smooth universe. There is a couple of remarks I wish to make about this picture. You may see as you go further, where you are located there is where we are in our galaxy, and these are the two different directions on the sky that I mentioned about. And you find that, the number of galaxies thin out as you go further away. This is just because of the fact that the telescopes that we have a finite resolution, which means at farther distances, it picks up the bright galaxies and ignores the weak, less bright ones. Okay? But if you look at close by, the number of galaxies within a certain circle that I can put there is roughly the same. More recently, over the last decade, there was a much larger survey of these galaxies, which is called the Slow and Digital Sky Survey. It looked up, almost 1 million galaxies and many quasars. And what I'm going to play a movie here, which was created out of the survey that was done. And you will see many objects, what SDSS, the Slow and Digital Sky Survey, did was observe in a few different directions of the sky with more sensitivity, with a higher resolution, so that it can look deeper in the sky. What you will see is that there are two yellow grids you will see. The first grid is at 1 million light years. Remember, one of the biggest nearby galaxies is called the Andromeda galaxies, is at a distance of about 2 million light years. So within 1 million light years, you will hardly see anything. In contrast, at 1 billion light years, you will see a phenomenal, almost all the galaxies that have been observed. At the end of the movie, towards the end of the movie, you will see a pattern in blue, yellow, and red, which is something called the cosmic microwave background. Please observe it. This plays a very important part of the story. I'm just going to play this movie and allow you to watch this. And the speed at which the movie runs is immaterial, okay? Eventually, what you will see is that, they would have observed in different directions in the sky, in the same fashion I showed in the previous figure, and they will turn it around to illustrate the fact that the distribution of galaxies is indeed reasonably smooth. So that's our galaxy. And we are going further and further from our galaxy. There are some nearby small galaxies which are immaterial. There is no audio here. That's the grid dimension. I don't know whether you can see far. There is a yellow grid coming up, which is at 1 million light years from us. Remember, the Andromeda galaxy is not, is beyond this. And you will see the Andromeda galaxy coming from the left very soon. I see some of you are taking pictures. These are available online. I can share all the details with you. There's the Andromeda galaxy comes in. So what you see is that space is largely empty, but on a sufficiently large scale, if you average out, there are roughly the same number of, galaxies everywhere. So what it means is that we are going farther and farther away, and there are many, many galaxies. And I mentioned they looked at different directions in the sky. Those are those cones, or the triangular regions. Again, don't worry about the color coding. Those correspond to different galaxies those are not essential for our arguments here. As I mentioned, they are turning the beam, and those are the, turning the image, and they looked at those 6, 7 different directions in the sky. And I mentioned eventually, there will be another grid that will come in. the universe is truly going through those dark, there is a period when the universe is actually dark. There is no, and then you see this pattern I mentioned about. We will talk about that as we go along. This blue, yellow, red pattern that you see is something called the cosmic microwave background. It forms a very integral part of our story. So I'll stop this movie and we'll continue with our lecture. So our goal is to explain what we observe, that pattern and this distribution of galaxies. That's the challenge before cosmology. Now, we will try to understand what other things we know about the cosmology. Can we say something about what the universe contains? It actually contains many things. Those again are not essential for our story. It contains two things we know: matter, that you and me are made of, and radiation or light. This is essential for our arguments here. It contains strange things which we don't know much about. Those are not essential for what I have to say. One of the easiest things you can observe about galaxies is their spectrum. As you know, if you have a body containing many elements and you heat up the body, it'll emit a continuous spectrum as shown on the top there. If it contains very specific elements, sodium, mercury or something, it will emit at given lines. These are called the emission spectrum. You can also have a situation where you can have a hot source and a cool gas in between, like it happens on the surface of the sun. There is relatively cool gas compared to the sun inside, the temperature inside the sun, and this cool gas can absorb the photons. It won't absorb all the photons, but it can absorb a large fraction of the photons, leading to something called an absorption line. So if you have a continuous spectrum and there is a continuous source emitting a continuous spectrum, and you have cool gas intervening between you and the source, you can have absorption spectrum. So if you look at a typical spectrum of a galaxy, which I will illustrate very soon, it will contain many of these. And in the context of the sun, I mentioned these are called the Fraunhofer lines. If you're an undergraduate physics student, you may actually be observing and doing some experiments measuring the wavelength of these lines. These are the typical spectra of galaxies. What has been plotted on the y-axis is what is called intensity, the amount of light coming in, roughly. And there are somewhere where it spikes, corresponding to specific transitions. There are spikes below, which correspond to the absorption spectra. And I can, take a spectrum of a nearby star, which is a typical spectrum in our galaxy, okay? And I can take the spectrum of these various galaxies I have, shown in the previous, in the set of slides that I had. And in fact, most modern telescopes, they know the distribution of galaxies, and in fact will have many, optical tubes, optical fibers, taking spectra of up to 50, 100 galaxies simultaneously. So these spectra are extremely easy to measure. You just need to take the light from a galaxy and send it through a prism, essentially, what we refer to as a spectrometer. Now, what was observed was as follows. If you have, you would have heard of the Doppler shift, the siren of the ambulance. As it approaches, its frequency increases. As it recedes, its frequency decreases. Light exhibits a similar behavior. If the source is coming towards you, its frequency increases, and if it is receding from you, its frequency decreases. If the frequency decreases, since the frequency and the wavelength are related by inverse relation through the velocity of light, the wavelength increases. And we can define something called the redshift. This will play again an important role. It's a simple concept for the students to appreciate. It is just the 1 plus z. Z is the redshift. It's a number, dimensionless number, is the ratio of the observed wavelength to the emitted wavelength. If the observed wavelength is larger, redshift is positive. Z is greater than 0. What it means is that, the source is receding from us. And as I will illustrate in a slide later, when you look at the spectra of galaxies around us, many of them are receding from us. and this is actual observations. What has been plotted are spectra from 4 different galaxies, and a particular line, we need not worry about what line that is, okay? Actually, what is known as the H-alpha emission line at a wavelength of about 65, 63 in the rest frame, okay? So this is a spectrum. On the left top is a spectrum. I guess you can see the mouse, okay? This is the left top, spectrum from a star in our galaxy. This is from a nearby galaxy where it has been shifted towards the red end of the spectrum, the larger wavelength. Here, the shift has been larger. Here, it is even larger. A trained astronomer can quickly see this spectra and identify what these lines correspond to. And what Hubble, almost a century ago, discovered was that when he looks at different spectra of different galaxies, all of them seem to exhibit redshift, indicating essentially that they seem to be running away from us. And this gives rise to the idea of the expanding universe. The universe, seems to be expanding, which is what is, seen as these redshift of these galaxies. The other thing which we need to measure is the distances to these galaxies, and Hubble found a certain connection between these two quantities. Distances are much more complex to measure in the context of cosmology. If it is 8 meters, 10 kilometers, or even 1,000 kilometers, I can measure with a ruler. I need a large enough ruler, but it is impossible to measure the distance to my nearby galaxy with the help of a ruler. So I need some strange ruler. The only ruler I can make use of, only thing I can use of, is the observed light itself. It's a relatively complex thing to define distance through light, and there are different measures, and it is also more non-trivial to measure that. I will not have time to talk about it, okay? But there are, astronomers have devised ways to measure distances to these objects. So what Hubble did was something amazing. He plotted, distance. Here it's on the x-axis on the left side, on the left figure, and the velocity. He assumed this is a Doppler effect. I will correct this impression very quickly. It has to be related to some concepts in general relativity that earlier speakers have spoken about. I will come to that in a matter of minutes. Okay? Here, Hubble thought of them as velocities. The same way the ambulance runs away, the larger the speed, the larger is the change in the frequency. He attributed certain velocities and drew a relation between them. He had a linear relation between them, which is called the Hubble's law. It is simple to understand. If you have velocity here and you have distance here and it's a straight line, the slope will have a certain dimension. And that dimension happens to be essentially 1 over time. And using the observations that he had, Hubble arrived at this slope to be 530 kilometer per second per megaparsec. What it means is that if there are two galaxies which are separated by a distance of about 1 megaparsec or so, they are moving with respect to each other at a velocity of 530 kilometer per second. Now, if you have these objects which are moving away and you try to run this is the idea of the expanding universe, and if you run this backward, what will happen? There may come a time where all the galaxies seem to be sitting on top of each other. This notion, this extended notion, is often referred to as the Big Bang. I will clarify some more points, conceptual points regarding the Big Bang as we go along, but this is the picture, the beginning picture you should have, that the universe seemed to be expanding. But there was issues with the Hubble data. Now, I mentioned that the slope of this curve, of this line has dimensions of 1 over time, and if I invert it, I will obviously have dimensions of time, which roughly indicates the age of the universe since the time when they were all on top of each other, which we refer to as the Big Bang. Now, what Hubble found was that that number he had obtained was, in conflict with the known age of the universe from observations of radioactive decay. That number, Hubble had got it wrong because we did not know the distances to these various galaxies very well. It has since been revised. This is on the right is a more modern version of the Hubble diagram. The original Hubble diagram appears in a small red corner at the bottom of the figure, if you can see it. And what one finds today is this called the Hubble constant, the slope of this curve. It happens to be 72 kilometer per second per megaparsec. Again, to emphasize, it means two galaxies separated by 1 megaparsec are moving away with each other with respect to each other at a speed of 72 kilometer per second. So you have an expanding universe. That is what it implies. Now, how do you describe the expanding universe? Well, on these larger scales and the greatest strengths that, such as black holes or very early stages of the universe, the Newtonian gravity ceases to be adequate to describe events that happen in these domains. And therefore, one need to go to general relativity. I presume some ideas about general relativity are introduced. There are two slides which are somewhat technical. I apologize for it. Okay. And what you have in general relativity, space-time is described something like what is known as a metric. Okay. And it is the metric which is changing. Space-time itself is changing. And this is what is manifesting as, the galaxies receding from each other. I'm going to skip this set of equations and move to this. The way you should imagine is the following. You can think of space-time as a balloon or the surface of a balloon. You can ask questions like, what is outside the balloon? Those questions we don't have answer to. We don't know. The space-time, our universe, is like the surface of a balloon. I should emphasize all these analogies have certain limitations. So you should, understand the limitations of the analogy as well. All these dots, yellow dots on the surface of these balloons are the galaxies. And if I blow the balloon, what happens? The distances between the galaxies are increasing. That is what is happening. This is the picture we have from Einstein's general theory of relativity about this expanding universe. It is not, we cannot attribute a velocity to the galaxies because somewhere it will actually cross the velocity of light. They are exhibiting this redshift because of the fact that the universe is expanding. This is what Einstein's general relativity tells us. And what has been illustrated, interestingly, in this picture is that there are, the photons which are going from one galaxy to another. As the universe expands, they turn red, blue to red, which means that wavelength increases. And this is actually what happens if you study the behavior of photons in general relativity. If I leave a photon, it will lose energy. If it loses energy, its wavelength increases, and that is what we observe as redshift of galaxies in the universe. And that is what this is about. I'm just going to skip this slide. So we have an expanding universe. We obviously have matter. What else does it contain? It evidently contains light. And what is amazing is the following. You can collect all the light together by all the stars that you observe. None of them contribute to the energy of radiation in the universe as much as something which is present everywhere in the universe. In this graph, what has been plotted is something like the amount of energy as a function of wavelength. I presume all of you are familiar with the fact that light comes in different wavelengths, the optical, the X-ray on one side, and the radio on the other extreme. What has been plotted is the energy density of radiation in different wavelengths. What you find is that it peaks around a certain place. It peaks around a certain place. It actually peaks in the microwave region of the electromagnetic spectrum. And what is amazing is that independent of where you look in the sky, there is this microwave radiation present. And for this reason, it is called background, which means independent of where you turn your receiver, microwave receiver, you will see this radiation. And therefore, it's called the background. It's microwave because it peaks in the microwave region of the electromagnetic spectrum. And as we shall see, it has a cosmic origin. We have this radiation, which is present everywhere, is actually vestige, remnants of radiation that the universe started with. And what is amazing is the following. I can measure the spectrum of the CMB. What has been plotted in this graph, this is indeed the spectrum. What has been plotted is this peak here has been plotted, has been zoomed in, plotted here, and this was measured by the Kobe satellite that I had mentioned about. It was measured by an instrument called FIRAS. In fact, this measurement, which was taken in '92, is still to be better today, and there are efforts, including efforts from India, to make better measurements. And another point to emphasize is that this is a perfect Planck spectrum, which, again, Professor Govindarajan mentioned, led to the origins of the quantum theory in 1901. And this is one of the best Planck spectrum. In fact, you cannot better this Planck spectrum even in your laboratory. And these error bars that you see have been enlarged 400 times so that it is visible in this graph. So what we find is that we are sort of bathed in a thermal distribution of radiation which seems to be present everywhere. This is often referred to as the cosmic microwave background radiation, and it has a temperature of about 3 Kelvin today. Now, another thing that what one finds is the following. This is a picture we will come to later again, okay? So what has been done is that you take a microwave receiver, all right, and you point in different directions of the sky, and you measure the temperature in different directions of the sky, and this is what you arrive at. I will explain what this is. I told you there is a temperature of about 3 Kelvin, 2.725 to be precise. I should emphasize the fact that cosmology was largely philosophical about a century and a half ago, and it was somewhat imprecise science about half a century ago. Over the last couple of decades, we have entered an era of precision cosmology where we talk about numbers. When I was a beginning student, PhD student, there was uncertainty of 50% or so in the various numbers that describe our universe. They are known to an extremely good precision today, and that is largely because of observations such as what we have illustrated in this picture. What does this picture represent? I mentioned that the CMB has a temperature of 2.725 Kelvin everywhere. Not quite so. If you are able to measure the temperature to a precision of 1 part in 10 power 5 up to the 5th or the 6th decimal place, what you find is that there are indeed anisotropies. Isotropy means the same in all directions, but there are anisotropies. There are small deviations from this exact of 2.725 Kelvin that I mentioned about, but they are at the 5th decimal place or so. And this is a somewhat old picture. There has been more precise measurements of the CMB anisotropies, which provide us with clues to the physics of the very early universe, as I will describe later. I apologize for this slide with equations, but there are a couple of essential points I need to emphasize. I mentioned we have matter, we have radiation. Beginning physics students will be able to appreciate the arguments I'm going to put together. You know that the density of matter goes as 1 over volume. So what you have are matter whose density goes as 1 over volume. What one can show using general relativity is that if you have a perfect thermal distribution of radiation in the universe, you know its energy density is given by the Stefan-Boltzmann's law. That is, sigma T power 4. What one can show is that the radiation density goes as 1 over the size of the universe. The A that I have here is roughly, you can say, the size of the universe, okay? Or to be precise, the distance between any two galaxies. Remember that distance keeps increasing as per the Hubble's law I mentioned. So what one finds is that the temperature of radiation in the universe goes as 1 over the size of the universe. And the energy density of the radiation goes as 1 over 4th power of the size, whereas the matter density we know goes as 1 over the volume or 1 over the cube of the size of the universe. Which means as you go back in time, the energy density of radiation as the universe shrinks in size, we have the expanding universe. As you run this movie backward, the universe will be shrinking in size. As the universe shrinks in size, what you find is that there comes an epoch when the energy density in radiation is much more than the energy density in matter. This is why I already referred to the fact that if you keep running the movie backwards, you will hit a big bang. What you find is that the early stages of the universe was hot because it was dominated by radiation than matter, and this is the term, this is the origin of the term hot Big Bang model. It's very popular, in fact. This is the snapshot of the very first screenshot of the very first image that appears in this popular sitcom, The Big Bang Theory. If you're a theoretical physicist, you can't but know about Sheldon. Okay, so this is the first shot, and which says our universe was in a hot, dense state. That is what it was. There was a Big Bang. We don't know much about it. What we know is that immediately after the Big Bang, or to be precise, sometime after the Big Bang, soon after the Big Bang, it was in a hot, dense phase. It expanded, it cooled, and slowly the density in the radiation fell faster than the density in matter, and we live in a matter-dominated epoch. Evidently, if the radiation was around it, it is very hot, not at 3 Kelvin, but at 3000 Kelvin, we would have evaporated today. Now, where does the CMB arises from? This is again fairly simple concept to understand. What you have on the x-axis as you go from left to right is time. Time is evolving in this fashion. This yellow fluid, this pattern yellow that you have are the photons. The energy density in radiation was high, which means there were a large number of photons present, and the photons also had very high energy. And what you have, these small green balls or electrons, these large red balls are protons. And these large green balls are neutrons, which don't play an important story here. So for instance, all these red balls, or if you're a physics student, you will appreciate they are the hydrogen nucleus. This, for instance, this 2 green balls and 2 red balls form the helium nucleus and so on, and there are electrons floating around. And why are the electrons not sticking to the protons? Okay, or these helium nucleus, for instance, because there are photons with large energy. As the electron tries to stick to the proton, they are knocked off by this energetic photon, and they are in an ionized state. But as the universe cools down, the photons lose energy, and there comes a time when the photons that you are seeing here, all right, do not have adequate energy to knock off the electrons. Okay, because the radiation has cooled and the energy in the photons is not adequate, is much, much lower than what is required to knock off the electron from the hydrogen and the helium atoms. And you can see these hydrogen and helium atoms forming on the right. You have the electron cloud around the nuclei, hydrogen and the helium nuclei. And what happens to these photons once these atoms form? The photons are free. There is nothing that stops them. And this free streaming photons that are coming to us, imagine, as you look back in time, as you look further and further, you are also looking back in time. And therefore, what you are seeing is that, these photons are coming to us from this surface, okay, where the photons stopped interacting with the electrons. And this is what we observe as the cosmic microwave. These yellow photons, which are screaming to the right, are the cosmic microwave background that we observe today. And how do we envisage this? It is very similar to the cloud here. If you know the idea of a mean free path, the distance, if you have an atom, which is moving here, it just goes like that, atom in a bath. If you see this dust particles illuminated by a ray of light, they will go like that. Okay? The average distance that these guys travel is called the mean free path. So you can imagine, think of this cloud here. What is happening here? Photons are not able to travel much within the cloud because there are many water molecules and other molecules present which scatter off their photons. But once they come free of this cloud, these photons are able to travel, and you are seeing this face of the cloud. And that's what you see as that pattern that you saw as anisotropies. And I can't prove those numbers. You have to take these numbers for granted. The age of the universe today, as we understand it, is about 13.7 billion years. The CMB is supposed to have occurred when the universe was about 380,000 years. So we are seeing these photons coming to us from very early stages of the universe, which in turn allows us to understand even earlier stages of the universe, as I will try to explain over the next few slides. And this is essentially what is referred to as the last scattering surface on the left. That is where the CMB comes to us, last scattering surface, because that is the last time the photons actually scattered with an electron, and it comes to us over this distance virtually unmolested. Now, we have understood the smooth universe. Okay? We have defined, what it means is that we have said there is matter, there is radiation, the universe was hot earlier, and so on and so forth. But the challenge before us is to explain those pictures that I had shown, where I had these clusters and clusters of galaxies. The question is, if the universe was smooth, how did it become unsmooth? What caused this deviation from smoothness? This is where the Hawking's ideas come in. And this goes back to an idea called inflation, and we need to understand why inflation occurred. What is inflation? So we have divided our universe into two parts. One, very early stages, where the universe was supposed to have been dominated by radiation, and later epochs where the universe is supposed to have been dominated by matter. And we roughly understand where the CMB comes from, where this separation occurs roughly. Now, what one finds is as follows. I mentioned that independent of which direction you observe in the sky, the temperature of the CMB is roughly the same, 2.725 Kelvin. And that is what has been illustrated here. I presume people have plotted some light cones before. Okay, I will just try to explain briefly what this figure does is as follows. The vertical axis is time. The horizontal axis is space. This is what was repeatedly drawn in those pictures in the movie that Professor Govindarajan showed. This is called a light cone because light travels always at the same speed. So if I plot the trajectory of light in x versus t, since it is moving with a constant speed, it will be a straight line. So you can draw two straight lines from today here to this epoch. This is time. This red band corresponds to this epoch I mentioned where the CMB comes from. The last scattering surface, this cloud where the cloud ends. This is where the cloud ends, okay? And this is today, and this is Big Bang in this hot Big Bang model. What one finds is that within this model, if you have any region in the sky which is separated by 1 degree, okay? Let us say two different directions like this, they could not have causally interacted. What it means is that these two endpoints could not have causally interacted. Okay, that is what these light cones represent. If someone is, this is technical, if someone is interested, I can clarify after my talk. This could not have happened. And this is where an important concept arises, and that is referred to as an inflation. I've skipped a slide, okay? I'll just go on to illustrate this in this manner. What has been plotted is time, okay? Is time. And this is the scale of the universe, the size of the universe. So this is how the universe expands in a radiation-dominated epoch. Its size increases. Notice time goes horizontally down. Okay? You need, if you want to ensure that the CMB has the same temperature in different directions in the sky, you need an epoch during the radiation-dominated stages, very early stages of the universe, where it undergoes accelerated expansion, rapid expansion, extremely rapid expansion. Can you see? Within a short span of time, I hope you note the times involved. This is 10 power minus 35 seconds after the Big Bang. Physicists are very ambitious. They believe they understand the universe as it was 10 power minus 35 seconds after the Big Bang. That's where most of my research falls in, for instance. And this is, close to few billion years. And the universe, if you assume that went through a rapid expansion, then you can overcome this problem I mentioned with the hot Big Bang model, where you cannot explain why the CMB has the same temperature in all directions of the sky. Now, there is something strange that happens. This, you need to understand general relativity in order to appreciate this idea completely. And this is where one of Hawking's papers that I mentioned about, where his contributions come in. What you have in the early universe are, yes, I'm done. Okay. What we have, I said you need to go through an accelerated expansion that cannot be achieved with matter and radiation. If you're familiar with electromagnetic theory, the electric fields are generated by charges. In a same sense, in Newtonian physics, it is matter that creates the gravitational field. An expanding universe is essentially a gravitational field. And according to Einstein's general theory of relativity, you need negative pressure in order to have an accelerated expansion. And this is achieved with various, what people refer to as high energy physics. This is what happens at very early in the universe. I told you that the temperature of the universe goes higher and higher as you go early in time. And at these high temperatures, ordinary physics does not apply. You need new types of physics. And there are, various scalar fields. One of its manifestation is the Higgs boson that you have heard about, come into play. And in these high energy theories, there exists matter which can drive this accelerated expansion. Another point is that at these very high energies, things cannot be classical. Professor Govindarajan mentioned that you need to take into account quantum effects, and these quantum effects come into play. These are complex ideas to explain within a limited span of time, but I will try to do so with the help of movies, with a couple of movies. What happens is that there are fluctuations, okay? And these fluctuations are what give rise to this, introduces deviations in the smoothness very early in the universe. I mentioned we are going to divide the universe in order to understand it as a smooth part, understand how it evolves, and then try to understand the evolution of this, deviations from that smoothness I mentioned. Okay, and the smoothness are essentially introduced by quantum fluctuations. You can think of a smooth water, okay, and you throw in some pebbles, and these waves that are generated by these thrown pebbles are what are essentially quantum fluctuations. These are, you can think of the early universe as, where there are many pebbles that have been thrown into a pond, and there exists very concrete ideas in physics that will allow you to evolve these quantum fluctuations into the pattern as anisotropies that we see in the CMB. This is a more recent version of the anisotropies in the CMB that, that I will soon talk about, and I'll stop this video and move to the next one. And what you have is as follows. There is another picture that we have. These are the pattern of the fluctuations in the CMB. I mentioned that these galaxies lie between us and the last scattering surface from which the CMB comes. And there are well understood theories that will evolve these small deviations from in temperature that are present in the CMB to form the structures of galaxies. Okay? I've been given about 5 minutes more. I will try to wind up in time. So this is a very popular picture illustrating our current view, timeline of the universe. What we have, this is again the horizontal axis is time, and what you have, the picture you have is this pattern that you see here, this blue and green and yellow pattern is the CMB, where it comes to us from. The age of the universe was about 380,000 years to be precise. The age of the universe today is about 13.7 billion years. And as I mentioned, it is these quantum fluctuations very close to the Big Bang that are supposed to have generated these pattern as anisotropies in the CMB. And one of Hawking's work, which is cited here, was on the idea of the generation of these quantum fluctuations. I should emphasize the following: this is well measured. This part of Hawking work can be tested with observation. I should also clarify it was not Hawking alone who had this idea. Hawking radiation was phenomenal. It was his own idea, but there were many others around the same time who had roughly the same idea, where they said quantum fluctuations can lead to patterns of anisotropies on the CMB. On the left, as these, remember I had shown this picture earlier about how different directions of the sky have different temperature. This is 25-year-old picture. This is on the left is roughly a 10-year-old picture. On the right is a 3-year-old picture. And we have increasingly accurate and precise measurements of the deviations from isotropy in the cosmic microwave background, which tell us, help us understand the physics as it happened very early in the universe. And, I will just play this, okay? So what you have is as follows. So if you introduce, this is a little tricky, I will try to. So think of this, what do you have? You have a smooth distribution of objects. Let each of these dots be galaxies. And what I have done is that, I have introduced a small deviation in smoothness. You can see these patterns. If it was ideally distributed smoothly, you will not see any pattern here. But the moment I introduce these deviations, galaxies, will attract each other. This is called gravitational instability. If I have a distribution of matter and they attract, each other gravitationally, what will happen is that they will eventually collapse to form one or more objects. And that is what the universe is supposed to have done. So what you have is as follows. I will play this. You start with small, tiny deviations, and here you see a pattern which beginning to resemble like the pattern of galaxies that you have seen earlier in some of my slides. And there is actually, this part is highly nonlinear, which means it is difficult to calculate on pen and paper. You have to run highly complex computational codes in order to understand their evolution, and we believe we have a rather good understanding. There are peculiar problems. We believe we have a reasonably good understanding of how the galaxies that I showed in the early pictures have formed. In the remaining, I will skip that part. I will briefly talk about the ideas on the origin of the universe itself. This was one of Hawking's, again, phenomenal concepts that were introduced. The concepts themselves are somewhat tricky for me to explain. These are two slides are extremely technical. I apologize for it, but I can't do justice to Hawking's contribution without introducing them. And I will be glad to answer as many questions as possible once I'm done with my talk. What Hawking tried to do was describe the universe as a whole in a quantum mechanical sense, not in a classical sense. There had existed an idea originally due to John Wheeler, again, who was mentioned by Professor Govindarajan, who introduced the idea of black hole, and someone by name Bryce David to describe the universe quantum mechanically. If you've learned some quantum mechanics, in quantum mechanics, the system is described by something called a wave function, which satisfies something like something called a Schrodinger equation, which is the equivalent of your Newton's second law in quantum mechanics. What they proposed was that the universe itself is, the wave function describing the universe itself satisfies a similar equation, which is called the Wheeler-DeWitt equation. And I will skip this third point. Let's proceed. It's somewhat technical again. What Hawking and co-workers in these two papers, they suggested was, we need to solve this equation. And one of the important things that you need to, when you solve these differential equations, is what are known as initial conditions or boundary conditions. They proposed a way of providing unambiguously this initial condition. And it involves complex theoretical ideas such as imaginary time, etc. And when you do so, there is a nice proposal where you can provide these boundary conditions, and it is called as the Hartle-Hawking wave function of the universe. And it provides you with a wave function to describe this entire universe, and you can, in some very crude manner, describe how the universe could have originated. And importantly, with another student of his by name Jonathan Halliwell, he could actually derive, show that in these models, inflation that I talked about, which was a classical picture, could arise from this complete quantum mechanical picture, and in fact can lead to those anisotropies in the CMB that I had mentioned. In contrast to ideas and inflation itself, these are somewhat difficult to test, and therefore, as I mentioned earlier, at this stage, they remain theoretical ideas. I'll just close with these two summarizing remarks. It's now commonly believed that it is the inflationary epoch, which I mentioned is the accelerated expansion during the very early stages of the universe, that is responsible for the generation of perturbations. What are these perturbations? I mentioned that the universe can be considered smooth very early in the universe, and it had tiny deviations from smoothness. These are called perturbations. And also, as I mentioned, the predictions, I didn't have time to discuss that. It's also a little technical. The predictions of the inflationary scenario are found to be remarkably consistent with the observed pattern of the anisotropies in the CMB. To emphasize, this is where Hawking played a crucial role. He was one amongst the few to recognize that the quantum fluctuations in the early universe can be responsible for these observed anisotropies. As far as the origin of the universe is concerned, it has to be explained in a supposedly quantum theory of gravity, where you essentially merge your quantum ideas with general theory of relativity. This is a work in progress, despite decades of effort through various approaches, ranging from, string theory, loop quantum gravity, etc. We are still seem to be far from converge on a quantum theory of gravity. Many challenges remain, and if our ideas of the origin of the universe will be on a much firmer footing if we can somehow quantize gravity. And that provides many interesting challenges, as Professor Govindarajan mentioned, on various fronts, and particularly from the context of cosmology, which is where your ideas of quantum gravity are likely to be tested, because those energy scales that are achieved in inflation are unlikely to be achieved in your LHC or even a super LHC. And cosmology is a good test bed to, for testing your ideas on gravity and quantum theory. With those remarks, I will thank you for your attention. I just have one more remark to say. I had mentioned the specific technical papers that this talk was largely based on, was motivated by, not based on necessarily. Here are a very few popular textbooks, and I would strongly urge you to look at them. The Steven Weinberg's First 3 Minutes is possibly the best popular science textbook that you can have, and I would strongly urge all physics students to try reading it. Thank you very much.
நன்றி டாக்டர் ஸ்ரீராம்குமார். இன்சிடென்டலி அந்த முதல் புத்தகம் ஸ்டீஃபன் வெயின்பர்க் அவர்கள் எழுதிய புத்தகத்தை ஸ்டீஃபன் ஹாக்கிங்ஸ் தன்னுடைய புத்தகத்தில் ஒரு நல்ல அறிவியல் நூல், பரந்துபட்ட மக்களிடத்தில் அறிவியலை எடுத்துச் செல்வதற்காக எழுதப்படும் ஒரு நல்ல நூல் எவ்வாறு எழுதப்பட வேண்டும் என்பதற்கான ஒரு உதாரணமாக அவர் எடுத்து கூறுவார். எவ்வாறெல்லாம் எழுதக்கூடாது என்பதற்கு எனக்கு ஏராளமான நூல்கள் தெரியும். நான் அதனை எல்லாம் சொல்லப்போவதில்லை என்று நான் சொல்லல், அவர் சொல்லியிருக்கின்றார். எவ்வாறு எழுதப்பட வேண்டும் என்பதற்கு உதாரணமான நூலாக ஸ்டீஃபன் ஹாக்கிங் அவர்களால் சொல்லப்பட்டது ஸ்டீஃபன் வெயின்பர்க் அவர்களுடைய ஃபர்ஸ்ட் 3 மினிட்ஸ் என்ற அந்த நூல். எளிதாக கிடைக்கிறது, இந்தியாவிலேயே எளிதாக கிடைக்கிறது. நீங்கள் படித்து பாருங்கள். படிப்பது தமிழில் வரல, நாங்கள் முயற்சி பண்ணிட்டு இருக்கோம். நீங்களாம் உதவி பண்ணால் தமிழில் கொண்டு வந்துடுவோம்.
This is actually remarkable because the first 3 minutes, முதல் 3 நிமிடங்கள் எதை சொல்றாருனாக்கா, பிக் பேங் ஆரம்பிச்சு நம்ம இப்ப இருக்கிறது வந்து 14 பில்லியன் இயர்ஸ் கழிச்சு அவர் என்ன சொல்றாருனாக்க, முதல்
1400 கோடி ஆண்டுகள்,
1400 கோடி ஆண்டுகள். அவர் என்ன சொல்றாருன்னா, முதல் 3 நிமிடங்களில் பிக் பேங்குக்கு பிறகு என்ன நடந்தது, அது ஜஸ்ட் we are able to say, அதை வந்து சொல்ல முடியுங்கிற ஒரு கருத்தை வந்து ரொம்ப ஆச்சரியமா இருக்கு. அந்த அளவுக்கு வந்து இயற்பியல் வந்து ஓரளவுக்கு இருக்கு. அதுல முக்கியமானது என்னன்னா, ஒரு வாய் ஸ்பெகுலேட்டிவ் மட்டும் இல்லை, அதுக்கு எக்ஸ்பெரிமெண்டல், அவர் சொன்ன இன்ஃப்ளேஷன் இதெல்லாம் சொன்னார் பார்த்தீங்களா, எக்ஸ்பெரிமெண்டல் எவிடன்ஸும் வந்து நமக்கு கையில் வருது. இப்போ அதுதான் வந்து இந்த மாதிரி சூழ்நிலையில் ஒரு 50 வருடங்களுக்கு முன்னாடி நம்ம இல்லை. இப்போ ஒரு 30-40 வருடங்களுக்காக முதல் 3 நிமிடங்களுக்கு பிறகு முதல் 3 நிமிடங்களில் என்ன நடந்ததுன்னு இப்போ என்ன கேட்குறாங்கன்னாக்க, முதல் நொடியில், அதாவது முதல் நொடியில பாதி என்ன நடந்தது, அதாவது பிக் பேங்குக்கு அப்புறம் அப்படிங்கிறது தெரியாது. அதுதான் கேட்டுக்கிட்டு இருக்காங்க.
டாக்டர் ஸ்ரீராம் அவர்களுக்கு இந்த நினைவு பரிசாக ஒரு நூலினை நண்பர் தியாகு அவர்கள் வழங்குவார். நண்பர்களே, தமிழ்நாடு அறிவியல் இயக்கம் பெரிய அளவில் இல்லை என்றால் மிகச் சிறிய அளவுகளில் இந்த அறிவியல் கருத்துக்களை தங்களுடைய கூட்டங்களின் மூலமாகவும் தாங்கள் வெளியிடும் நூல்கள் மூலமாகவும் பரவலாக தமிழகத்தின் எல்லா மாவட்டங்களிலும் எடுத்துச் சென்று கொண்டு இருக்கிறது. இந்த பணியை உங்களுடைய பங்களிப்போடு நாங்கள் மேலும் திறம்பட செய்வது இயலும் என்று நாங்கள் நம்புகின்றோம். இன்றைக்கு இங்கு அளிக்கப்பட்ட உரைகளில் சில முழுமையாக ஆங்கிலத்தில் இருந்தது என்பதனை நாங்கள் உணர்கின்றோம். சில கருத்துக்களை நேரடியாக தமிழில் சொல்வது அந்த துறையில் இயங்கிக் கொண்டு இருக்கக்கூடிய இந்த அறிவியல் வல்லுநர்களுக்கு சிரமமாக இருக்கின்றது. இது வந்து ஒரு யதார்த்தம். ஆனால் முடிந்த மட்டும் இந்த கருத்துக்களை அவர்கள் அளவுக்கு இல்லை என்றாலும் அதனுடைய ஒரு எளிமையான வடிவில் தமிழில் எடுத்துச் சொல்வதற்கு தமிழ்நாடு அறிவியல் இயக்கம் தயாராக இருக்கிறது. தமிழ்நாடு அறிவியல் இயக்கத்தில் இந்த கருத்துக்களை ஒரு சிறிய அளவில் அறிமுகம் செய்யும் அளவிலாவது தமிழில் கூறுவதற்கு திறமை கொண்ட, அதற்கான பயிற்சி கொண்ட நண்பர்கள் இருக்கின்றார்கள். உதாரணத்துக்கு தமிழ்நாடு அறிவியல் இயக்கத்தினுடைய சென்னை மாவட்ட தலைவரான டாக்டர் ரவிக்குமார் அவர்களும் ஒரு இயற்பியல் துறையில் முனைவர் பட்டம் பெற்றவர்தான். அவர் பல விஷயங்களை தமிழில் எடுத்து கூறுவதற்கு வல்லமை கொண்டவர். உங்கள் கல்லூரியில், உங்கள் பகுதியில் இது போன்ற நிகழ்ச்சிகளை தமிழில் சிறு அளவில் நடத்துவதற்கு நீங்கள் முயற்சி செய்தால் நாங்கள் உடன் இருந்து அதனை நடத்தி தருவதற்கு நாங்கள் தயாராக இருக்கின்றோம். அந்த வகையில் நீங்கள் எங்களோடு இணைந்து பணியாற்றுவதற்கு ஏராளமான இடங்களும் வெளியும் காலமும் இருக்கிறது என்பதனை சொல்லிக்கொண்டு உங்களை தமிழ்நாடு அறிவியலோடு இணைந்து பணியாற்றுவதற்கு நாங்கள் அன்புடன் அழைக்கின்றோம். நீங்கள் செல்லும் பொழுது உங்களுடைய ஃபீட்பேக், உங்களுடைய இந்த நிகழ்ச்சி பற்றிய கருத்துக்களை உங்கள் பெயர், உங்களுடைய மின்னஞ்சல் முகவரி, உங்களுடைய தொலைபேசி எண்ணோடு அளித்தால் மேற்கொண்டு நாம் இணைந்து பணியாற்றுவதற்கு வாய்ப்புள்ளதாக இருக்கும் என்பதனை நாங்கள் உங்களுக்கு சொல்லிக் கொள்கின்றோம். தயவு செய்து எங்கள் பணியினை பாராட்டும் விதமாக எங்கள் பணியினை இருக்கும் குற்றங்குறைகளை கூறியாவது, உங்களுக்கு என்ன பிடிக்கவில்லை என்பதனை கூறியாவது அந்த ஃபீட்பேக் ஷீட்டை, அந்த உங்களுடைய கருத்துக்கள் அடங்கிய தாளை எங்களுடைய நண்பர்கள் இந்த வாசலில் இருப்பார்கள், அவர்களிடத்தில் தயவு செய்து நீங்கள் அளித்து செல்ல வேண்டும் என்று மிகவும் தாழ்மையுடன் கேட்டுக்கொள்கின்றேன். தற்பொழுது இறுதியாக முறையான நன்றி நெறிவில் அதற்காக நண்பர் விஜயன் அவர்களை அழைக்கின்றோம். நாங்கள் இந்த நிகழ்ச்சியை முடித்தவுடன் ஒரு அளவுக்காவது விவாதம் என்ற வகையில் அவர்களுடைய கேள்வி பதில் நிகழ்ச்சிக்கு நடத்த வேண்டும் என்று ஆசைப்பட்டோம். ஆனால் 8:30 மணிக்கு நாங்கள் இந்த அரங்கத்தை காலி செய்து அளிக்க வேண்டிய நிர்பந்தத்தில் இருக்கின்றோம். அண்ணா நினைவு நூற்றாண்டு அந்த நிர்வாகம் எங்களுக்கு இந்த அரங்கத்தை அளித்ததோடு இந்த நிகழ்ச்சியை எங்களோடு இணைந்து நடத்துவதற்கு, அவர்களுடைய நிகழ்ச்சியாக நடத்துவதற்கு அனுமதித்ததற்கு நாங்கள் நன்றி கூறும் விதத்தில் அவர்களுக்கும் நன்றி கூறி மற்றவர்களுக்கும் நன்றி கூற நண்பர் விஜயன் அவர்கள் வருகின்றார்.
நண்பர்களே, மிகச் சிறப்பான ஒரு நிகழ்ச்சி நடைபெற்று முடிந்திருக்கிறது. இந்த நிகழ்ச்சியினுடைய வெற்றிக்கு பின்னால் பல நபர்கள் உழைத்திருக்கிறார்கள். அவர்கள் எல்லோரையும் பட்டியலிட்டு நன்றி கூறுவது என்பது மிகவும் சிரமமான காரியம். இருந்தாலும் ஒரு சிலரை குறிப்பிடாமல் தவிர்க்க முடியாது. என்னுடைய முதல் நன்றி இந்த அண்ணா நூற்றாண்டு நூலகத்தினுடைய இணை இயக்குனராக பணியாற்றி கொண்டிருக்கும் திரு நாகராஜன் முருகன் அவர்களுக்கு நான் நன்றி செலுத்த கடமைப்பட்டிருக்கிறேன். அவருடன் உரையாடி இந்த அரங்கத்தை எங்களுக்காக வாங்கும் பொழுது அவர் நிச்சயமாக நீங்கள் நன்றாக செய்வீர்கள் என்ற நம்பிக்கையோடு நான் உங்களுக்கு இந்த அரங்கத்தை உங்களுக்கு அனுமதி அளிக்கிறேன் என்றார். அவருக்கு எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறோம். அத்துடன் இந்த நூலகத்திலே பணியாற்றி கொண்டிருக்கும் தலைமை நூலகரான திரு தினேஷ் அவர்களுக்கும், நூலகராக பணியாற்றி கொண்டிருக்கும் காமாட்சி அவர்களுக்கும் எங்களுடைய நன்றியினை உரித்தாக்கிக் கொள்கிறோம். மூன்றாவதாக இந்த நிகழ்ச்சியில் பேசிய அனைத்து அறிவியல் வல்லுநர்களுக்கும் என்னுடைய நன்றி. குறிப்பாக டாக்டர் முருகன், டாக்டர் கோவிந்தராஜன், டாக்டர் ஸ்ரீராம்குமார் ஆகிய மூவருக்கும் தமிழ்நாடு அறிவியல் இயக்கத்தின் சார்பாக எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறேன். அதை அடுத்து இன்று நடந்த நிகழ்ச்சியினுடைய மொத்த செலவையும் ஏற்றுக்கொண்ட நண்பர் இளங்கோ, ராஜம் பில்டர்ஸ் உரிமையாளர் இளங்கோ அவர்களுக்கு எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறோம். இந்த நிகழ்ச்சிக்கு தலைமை தாங்கி நடத்திய பாக்கு ராஜன் அவர்களுக்கு தமிழ்நாடு அறிவியல் இயக்கத்தின் சார்பாக எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறோம். அத்துடன் நிகழ்ச்சியை ஒருங்கிணைத்து கொடுத்த சுந்தர் மற்றும் இதர தொண்டர்களாக பணியாற்றிய அனைவருக்கும் தமிழ்நாடு அறிவியல் இயக்கத்தின் சார்பாக என்னுடைய நன்றியை தெரிவித்துக் கொள்கிறேன். இந்த நிகழ்ச்சி துவங்கும் முன் இந்த நிகழ்ச்சிக்கு வந்து இதை துவக்கி வைக்க வேண்டும் என்ற ஆர்வத்துடன் இங்கே வந்திருந்த சென்னை மாவட்ட முதன்மை கல்வி அதிகாரி திருநிறை செல்வி அவர்களுக்கு எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறோம். தமிழ்நாடு அறிவியல் இயக்கத்தின் மாவட்ட தலைவராக செயல்பட்டு கொண்டிருக்கும் டாக்டர் ரவிக்குமார் அவர்களுக்கு எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறோம். அதையும் தாண்டி 3.5 மணி நேரமாக பொறுமையாக இந்த நிகழ்ச்சியில் பங்கெடுத்த உங்கள் அனைவருக்கும் தமிழ்நாடு அறிவியல் இயக்கத்தின் சார்பாக எங்களுடைய நன்றியை தெரிவித்துக் கொண்டு இந்த நிகழ்ச்சியை முடித்து வைக்கிறோம். நிச்சயமாக உரையாடல் பகுதி இருக்கிறது. அது நாங்கள் ஒரு முறையானபடியாக செலுத்த முடியாத செய்ய முடியாது. ஆனால் இங்கே இருக்கிற அறிவியல் வல்லுநர்கள் நீங்கள் கேட்கும் கேள்விகளுக்கு பதிலளிப்பார்கள். அவர்கள் இன்னும் 1 மணி நேரம் கூட இங்கே இருப்பார்கள். சந்தேகமுள்ள நபர்கள் இங்கே வந்து அவர்களுடன் உரையாடுமாறு நாங்கள் கேட்டுக்கொள்கிறோம். அடுத்த நிகழ்ச்சியில் நாங்கள் நடத்தும் பொழுது கண்டிப்பாக இந்த பேனல் டிஸ்கஷன் என்பது சிறப்பாக அமைவதற்கு நாங்கள் உறுதியளிக்கிறோம். உங்களுடைய ஒத்துழைப்பு எங்களுடைய நன்றியை தெரிவித்துக் கொள்கிறோம்.